In my previous videos of the Solow model, we're going to do a quick recap of them quickly. So let me just do a quick recap of the Solow model without technology. I'm not going to go through it all, just so we get an idea. So we had this production function that was a function of capital and labour. So what does that mean? That meant that our inputs to create output were just capital and labour. And for example, you saw something like this. Capital to the 2/3, labour to the third. And then we put it into intensive form. We put it in per capita terms, per labour. So we divided everything by L as following. So then we got it in little letters and we got something like this. Okay, so this was what we had done before. And then what we wanted to do is that we know that it was a simplified economy where we have two options. We consume or we save, and if we're saving, that's the same as investing. And we cared a lot about what was known as steady state. So we cared about something called steady state. And this is when our capital stock will stop changing. So the change in our, capital stock per worker was 0. And if we remember what the equation was for that, then it was this, right? It was the change in K was equal to, well, we've got two options. We can save, which is the same as investing. And if you're investing in capital, so capital's growing. So S of Y, so we save a function of our outputs, and then minus any kind of like loss. And I think in the previous one we just had depreciation, but I could have had labour growth in there as well. So I'll put both of those in. And it was something like that, right? And we had to figure out when that was 0, and that was your steady state, and you could find out the steady state level of capital per worker. And then we continued on and we did the golden rule and so on and so forth. So that is what we've done in the previous video. So if you're not confident with that, then please go and recap on that before we move on. So you might be thinking to yourself, well, brilliant, we're done, like, that's great, why do we need to do anything else? Well, if we can remember the outcome in this scenario, what was happening? Well, firstly, we cared about per worker, we cared about in per capita terms, because obviously countries are always, loads of countries are of different sizes, and it's not really fair to just compare them like that. Because if you have more workers in your country, if it's a big country, then you would expect for them to be able to produce more output. So we care about it in per capita terms. But what we were seeing is that once we got to steady state, what was happening with Y over L? Well, we knew that L would be growing at rate N, and then means Y, because it has to be the same, there's no growth, we're in steady state, Y also grows at rate N. So essentially, once you've reached convergence, there was no growth here, okay, which a capital stock wasn't changing. And we would quite like to see, well, is there possible for us to model something similar where we can have sustained output per capita growth? So this is where technology comes into it. So I'm going to keep that there if I can, and maybe I need to get rid of it when I need a bit more room. But then we need to think about bringing in technology. So hopefully you've been seeing in class already, you're saying, well, we can adapt our production function slightly. Now, there are two ways to do it. The way I'm going to do it is what's called the Harrod-neutral or the labour-augmented one. There's also a Hicks one, but let's do I think the labour-augmented is one that kind of like is a little bit more realistic. So what do we have now? Well, we have the output, like we had before, is a function of capital. So we've seen this as standard. But this time, instead of labour, we have it multiplied by A. And this A here is kind of known as like the state of technology, the technological progress, the state of technology. So we follow something that we've done before. We clearly can't just leave it in output terms. You want it in intensive terms. But now, instead of dividing by L, we divide by AL. So Y over L is per capita. Y over AL is what's known as output per effective worker. output per effective worker. Okay, so basically it's this idea that each person is sort of able to use technology and we care about how effective they are, so output per effective worker. Well, let's follow this through then. So if we were to follow this through, we would have something like the following. So I'm going to do this in algebra terms and then I will make up a numerical example for you. So let's just pretend for the minute this looks like the following. We're going to have k to the alpha and al to the 1 minus a. The brilliant thing is once you get your head around the earlier videos, this is somewhat trivial. It comes out the same. The only great thing is at the end we can talk about sustained growth, which is what we want to talk about. Okay, so we are going to divide this. We're going to divide this by a over l, because what we do to one side, need to do to the other, or they're not balancing. So let's sort this out then. So what do we have? We have al to the power of 1 minus alpha, and we have al here, which is technically to the power of just a 1. And we know from GCSE Maths, rules of indices, that I can just subtract these powers. So what am I left with then? I'm left with k to the alpha and al. So I've got 1 minus alpha minus 1, which is going to be negative alpha. Okay, we can neaten this up a little bit. So y over al is going to be the same as k to the alpha over al to the alpha. If it have a negative indice, put it on the bottom of the fraction and make it positive. So we have this. And what we're going to do is, because this is a little bit cumbersome to write out all the time, I'm going to write it in what's known as intensive form, so little letters, and I'm going to do a little y. I'm actually going to put a tilde on it, just because I want to differentiate that this is different from what I did in my previous video, and I'm going to put a little tilde on here, and that's that. So this means output per effective worker is equal to capital per effective worker, and it's to the power of alpha. Okay, so that is our production function in intensive form per effective worker. So we can follow this through now to figure out the rest. So let me get rid of this little recap on the side and see where we go. Okie dokie, so we have now our production function in intensive form, and again we're going to care about steady state, right? So we are again caring about the capital stock changing, but now, whereas before you were caring about the capital stock per capita, it's all the same equations, it's just this time it's essentially the change in the capital stock per effective worker. So your equations haven't changed. If you know them for the previous video, you know them for now. So I'm going to write out the exact same equation that you're used to seeing, apart from I'm going to put tildes on everything. Now I'm going to write this. So maybe what's looking a bit different is this in here, right? This here. You were definitely used to seeing depreciation. Potentially you were used to seeing N, so depreciation is the rate at which capital depreciates. N was the rate at which my labour grows, the labour force grows. Maybe you weren't used to seeing G. So what is G? G is the growth rate of technological progress. Growth rate of, I'm just going to say tech. So you might be saying to yourself, well, hang on a minute, I'm a little bit confused now. Why is it that if my labour force grows, or why is it that if we're essentially improving technology, why is that taking away from the capital stock? Why is that taking away? Well, if we look at two things, if we go back to just y over L, if we increase our labour force, so if n is, right, if we've got a value for n, so the labour force is growing, L is getting bigger, okay? Well, if L is getting bigger and y is staying the same, this fraction overall becomes smaller. It makes sense, right? You've got this output, you've got this capital, or even just k over L, you've got this capital, I'll do k, it makes more sense. We've got this capital stock, but now I've got more people. Therefore, like, if I divide that by a bigger number of people, overall it's fallen. So it's taking away from our, because remember, this isn't just the change in k, it's the change in, if we're doing just per capita, it's the change in capital per capita, okay? So similarly, with this one here with the tilde, if we have a capital stock and we're dividing it by our effective workers, and we're knowing that the state of technology is improving, so basically people are becoming more effective, but the capital stock isn't increasing, you've got a bigger denominator and a smaller, a numerator that's unchanging, and therefore this improvement in technology is causing the change in the capital per effective labour to fall, okay? So that's why it's a subtraction. Now, that doesn't mean that having technology in our production function is a bad thing and it's going to be bad. It actually does go on to be positive because it shows that it gives us sustained growth. But just in terms of k over AL, then it's a taking away, because this is what our change in our capital per effective worker is, okay? If instead we just cared about k over L, then we'd see something different, but that's not what we're measuring here. And this will make more sense once we get near the end of this. So let's rub that out and let's just continue on with what we were doing. So we know from our old videos that in steady state, so in SS, we know that the change in the capital stock per effective worker must be equal to 0, okay? We know that. This has not changed. And what else do we know? So, well, we can rewrite this kind of thing, right? We can rewrite this as S, and we know what y tilde is. We figured it out here. We figured it out that it's k tilde to the alpha. So we could write that as that if we wanted to, okay? So we've got our equation for steady state, which is fantastic. And you can also draw your graphs. Is that what you want to do? The graphs haven't changed in terms of their shapes or anything like that. Just remember that on your axes now, it's all per effective worker. So this is little k tilde, whereas before it was capital per capita. It's now capital per effective worker, and then it's all your output per effective worker. So y tilde, savings, and so on and so forth, okay? So these things haven't changed. You still have a straight line for this delta plus g plus n, that. You still have your, if we assume that alpha is less than 1, we still have that, and then we still have this, okay? So this example, just because we've included A, hasn't really changed anything yet. So if you were okay doing it before, you're going to be okay doing it now. The only thing is at the end is when we start talking about how growth in output per capita has changed, okay? So let's figure this out. Let's do it algebraically, and then we'll do a nice numerical example. Okay, so we want to figure out what the level of capital per effective worker is in steady state, okay? So what do we know then? Well, we already know that in steady state these equal to 0, so we can just set them equal to each other. So I have my savings equals delta plus g plus n of that. Again, when we do a numerical example, maybe we'll change it slightly so that you don't have all of this, but let's make it as hard as it can be, and then we can make it easier. So what's the aim of the game? The aim of the game is to eventually just get k tilde equals, okay? So what am I going to do? I am going to divide by d plus g plus n. It doesn't really matter which way round you do it, it's just the way I'm doing it. As long as you pick one side to get all your k's onto, you're going to be fine. D plus g plus n equals k tilde. Okay, I now need to divide by k tilde alpha. So s over delta plus g plus n equals k tilde, we're going at a funny angle right now, over k tilde alpha. Okay, we're getting there. Let's make a bit more room and then we can finish this. Okay, so we need to sort this out. So what do I have? I have s over delta plus g plus n equals, again, rules of indices, happens a lot. We've got a little secret 1 sitting there. We're going to subtract them because we're dividing. So I'm going to have k tilde to the 1 minus alpha. So we're nearly there, apart from I want k tilde equals. I don't want k tilde 1 minus alpha equals. So if I gave you k tilde squared and I wanted just k tilde, you'd tell me to square root, wouldn't you? Well, I can just do a square root because you know what that is. But also, technically, square root in terms of like indices is the same as a half. I could do anything to the power of a half, and that means I'm square rooting. So as long as you do it with a fraction of what you've got, that means you're undoing that root. So what this is then, this is k tilde equals this fraction all to the power of 1 over 1 minus alpha. I done something wrong. Okay, so in steady state, this is what k tilde equals. I mean, we haven't put any numbers in, but if you can follow this algebraically, you can definitely do it with numbers. It gets a little bit easier with numbers. So that would be our capital per effective worker in steady state. Maybe there are other things that you want to know. Maybe you want to know what the output per effective worker is in steady state. That's fine, we know that too. Because we knew that output per effective worker was the same as the capital per effective worker to the power of alpha. Well, let's do that. We've got capital tilde, so we're going to do that. We're going to do s over delta plus g plus n. And we need to raise all of this. We need to raise all of this to the power of alpha. Now, back to GCSE school maths. If we have an indice on the outside and we want to bring it in, we multiply our indices together. So I've got 1 over 1 minus alpha multiplied by alpha, which is basically alpha over 1. So this is going to be rewritten as this. Alpha over 1 minus alpha. Okay? And this is your output per effective worker in steady state. So we've got that. What else could we have? Maybe you want to know what consumption per effective worker is in steady state as well. So let's write that down as well. Let me make a bit more room and then we can write that down. Okie dokie, so what we now want is we just now want to know about consumption. Well, let's think about it logically for the minute. My consumption is equal to my output minus my savings, because I remember I said it was a very simplified model where we produce and we either consume or we save. So what I've produced, I take away my savings and the rest must be what I consume because that's my only options. Okay, well, we know this then. We know what output is. So consumption per effective worker is my output. Well, we know what output is in general. So we know that output in general is this, and minus our savings. And we know what savings is. We know savings is this. So this is just your general equation for consumption per effective worker. Now, if it was I wanted to know what this was in steady state, if I wanted to know what my consumption per effective worker was in steady state, then I just need to fill in for my capital per effective worker in steady state. So I need to fill in for this, okay? So that's how we'd figure that out. We'll make this more clear when we do a numerical example. So that would give you all of those. And then lastly, perhaps that we want to talk about something called the golden rule. Maybe you want to talk about something called the golden rule. Well, if we remind ourselves what the golden rule was the steady state level of capital where consumption is maximised. And we need to think about how on earth we maximise consumption. So we need this to be a maximum. We need this to be a maximum. Okay, well, it's the same what you did in the previous videos. We had these graphs, we had these curves, we had this straight line here, we had this output, n plus delta plus g of okay, we had these. This was my steady state. This is my steady state level of capital. And, well, we already know that in steady state, SK of alpha has to equal n plus delta plus g of that, because that's when the capital stock's not changing. And we want to maximise the gap between here and here. We want to maximise this gap. Well, how do we do that? We take this straight line, we pull it back until it's tangential to there, and this would tell me what capital per effective worker needs to be to maximise consumption. Algebraically, I'm scooting over this quite quickly just because it follows the exact same what we did in the previous video. It's you differentiate your output function, and that equals the slope of that line, d plus g, okay? We'll make this all more clear when we do an example. So we've got that going on. Perfect, okay, so let's clear this. Let's have a little chat about what this means, and then let's do a numerical example. So what have we got going on here? We've got y over al. Why is this technology really, really fundamental here? Well, we've got y over al, and we know that this is constant. This is constant in steady state, right? Okay, well, how is that going to work out? So let's pretend we've got a model where we have technological progress growing at rate g. So we have rate g. We have the labour growing at rate n. Okay? So what does this mean? Well, if we look at this here, if we look AL, we know that this grows at a rate of G, this grows at a rate of LN, sorry. So we know that these two are growing at this rate. Well, Y must grow at the same rate as the denominator. The numerator must grow at the same rate as the denominator in order for this to be constant. If one of them grows faster than the other, then you're no longer constant, and that goes against the rules of steady state. So if that's the case then, if this is growing at essentially a rate of G plus N, so we've got a rate of G and a rate of N, this must also be growing at a rate of G plus N. That's the only way that works out. If you're denominator is growing at a rate of g plus n, the numerator must also grow at a rate of g plus n, and therefore we're constant in steady state. So you might think, well, hang on a minute, I've done all of this and I've got no further along as to like what I did in the previous video. Well, you have, because that's not really what we care about. What we really care about is output per capita. We don't care about output per effective worker. Okay, well, the thing is, you've just told me that output itself is growing at a rate of g plus n in this model. You know that, okay? Labour is growing at a rate of n. As we can see, our numerator is growing at a faster rate than our denominator. Because in steady state, this expression here is being constant. It's not said anything about this. It's not said anything about this. So what does this mean then? This means overall, overall, this is growing at a rate of g. This fraction, so output per capita grows at a rate of g. If you take away the two growth rates on the numerator and the denominator, you get the overall growth rate. So as we see here, this denominator is growing at a rate of g plus n, the numerator is growing at a rate of g plus n. Take them away from each other, you get a zero growth rate, which works because in steady state we're a constant, we're not growing. But now, if we have technological progress and it's growing, and then we try and see what happens in output per capita, we see that actually the numerator is growing more than the denominator, and therefore overall we're growing at a rate of g. So by including technological progress, by doing this labour augmenting style into a production function, we now have sustained growth. We have sustained growth. So the Solow model beforehand was saying that, well, actually we can grow, but we'll reach a point where we'll converge and then output per capita is not growing, and that's that. But we wanted to be able to do a model where, well, hang on, would it be possible to have sustained growth in output per capita? And it is. Even though in output per effective worker there's not sustained growth, that's fine. We care about output per capita. You know, a lot of the measures, GDP per capita, that's the thing we care about. And we can have sustained growth, and it would be sustained growth at a rate of g. Okay, so that's why this is fundamental, and that's why technological progress is important. So now let's just do a numerical example that I've made up, and in case that's what you were caring about. So, let's have a really made up example here. I'm going to give you a production function, and I'm going to have the production function of this. So I'm going to have y equals capital to a third, al to the power of 2/3. So we can automatically see it's labour augmenting because our technology is multiplied by labour. And I'm also going to tell you that what we're going to have is we're going to have a savings rate in this economy of 0.2. We're going to have a growth rate of technological progress growth rate of 0.4. I'm going to have depreciation of 0.1, but I'm going to say that there's no population growth, okay? It's 0. If I gave you that, it's very easy where that just substitutes in. So the first step is put this into intensive form, but now we mean it in per effective worker terms. So I'm going to divide everything through by AL. So we're going to follow what we did algebraically. Instead of alphas and that now, we have numbers, okay? So what's this going to equal? This is going to equal k to the third over al to the third, and therefore I can actually write it in terms of little letters. I can say y tilde equals k tilde to the third, okay? Remember when we did this algebraically, we had this, and alpha was here, so this follows. All I do now is take what I've done algebraically and put in for alpha. So it's very straightforward. If you understood the algebra, you definitely understand this. Okay, so I have my output per effective worker. Fantastic. Okay, and now the question may be, after you've done that, the question may be, can you find for me what the capital per effective worker is in steady state? So, in steady state, what do we know? We know sk tilde of a third must equal delta plus g k tilde. Remember in algebra terms we had an n in there? Well, n is just 0. So that's that. So this, what does this boil down to? This is sk tilde to the third equals, oh, and I can fill in for s. Let me just do that, that's going to confuse some people. So 0.2 k tilde to the third equals 0.5 k tilde. And the aim of the game, rearrange this, find k tilde. Once you've done that, you've got the capital per effective worker in steady state, which is, you know, quite a common question to be asked. So let's sort this out. I'm going to do 0.2 divided by 0.5 and k tilde divided by k tilde to the third. Okay, and I'm going to neaten this up, so let me go over here. So this is when you can whack a calculator out if you wanted to do 0.2 divided by 0.5. It's actually 0.4. So we're going to get 0.4 equals, so I'm going to have 1 minus a third, so I'm going to have k tilde to the power of 2/3. So we're very nearly there. I just need to undo this power to 2/3. So you either need to do the 2/3 root of 0.4, which you actually can just type into your calculator. You can just type that into your calculator. Or you can type in 0.4 to the power of 3 over 2. And that's the same thing as undoing to the power of 2/3. So we know that k tilde, which is capital per effective worker in steady state, is equal to 0.4 to the power of 3 over 2. So what does that equal? Let me type that into a calculator and see what we get, because I have just made these numbers up. And I get k tilde. Maybe I'll do a little star there to indicate we're in steady state. 0.25 to 2 decimal places. So that is what my capital per effective worker is in steady state. Okay? Fantastic. So let's clear that. I'm going to rewrite this up here though. This is in steady state. It was 0.25 to 2 decimal places. Obviously, you need to follow whatever rules you're given about rounding. So we've got that. What about if I want to know what the output per effective worker is in steady state? Well, I know that y tilde is the same as k tilde to the power of a third, but I want it in steady state, so all that means now is y tilde in steady state must be whatever my k tilde in steady state is to the power of a third. So 0.25 to the power of a third. So again, whack that into a calculator and see what you get. I get, to 2 decimal places, I get 0.63 to 2 decimal places, okay? So we've got that, and then maybe you want to know what consumption per effective worker is in the steady state as well. Well, that's easy to do because we know that that is your output per effective worker in steady state minus your savings of your output in steady state. So we've got that. So what do we have there then? We have 0.63 take away 0.2 times 0.63. So we save 20%, 0.2, of our output, but we consume, we've actually produced 0.63. So type that into a calculator and hopefully you get 0.5, let's be consistent, 50 if we're doing it to 2 decimal places. Okay? So we've got that, we've got a few things here. We've got our capital per effective worker in steady state, we've got our output per effective worker in steady state, and we've got our consumption per effective worker in steady state. Maybe you want to show this graphically, maybe that's the next question you get asked. That's easy to do. Let's do that. So what have we got then? We've got this little straight line here, which is delta plus growth rate, because we don't have n. So what was that? 0.5, right? So that was 0.5 of capital, k tilde. We've got this output production function here. Obviously, you're going to draw this so much nicer than I am. And then we're going to have this here. Okay, well, what do we know? We know that in steady state, we know that sy tilde is equal to, is where it crosses, it intersects our straight line. So this comes down here, and this is now our k star tilde, so this is 0.25. This is our golden rule, this is our steady state level of capital per effective worker. You could follow this up, and you could follow this across to tell us what y, so this could be y, it's showing loads of things, but this is y. So what did we say that was? We said that was 0.63. This was 0.63, and the difference between these two curves here is our consumption, and we know what that is. We know that's 0.5, okay? So you've not only done it mathematically, you've now shown it diagrammatically as well. And then potentially maybe the last thing that you want to do is you want to figure out the golden rule. So let's have a little look at that. So golden rule. What do we need to do then? We need to firstly figure out what f dash of that is. So what is the differentiation of our production function? Let me just write this back up here so we don't forget what it is. It was this. So we just need to differentiate this with respect to k, little k. Okay, we can do that. That's easy. So we can do this. We're going to bring that power down. I keep doing a y when I'm not meant to. And we're going to subtract 1 from that power. So we have that essentially the slope of our production function, or it differentiated, is this, okay? And we know that in the golden rule, we need to set that equal to delta plus g, plus n if you have it, but we don't, okay? So that means that equals 0.5. And then what we need to do is we need to rearrange for k, and that gives us the steady state level of capital needed in the golden rule, so when consumption is maximised. So let's try and figure that out. So the easiest way to do this first, maybe to rearrange this, would be I'm going to write this as this. If you ever have a negative power, do 1 over it, and then you can write it as positive, just because that makes life a little bit easier. Okay, I'm going to multiply by k tilde 2/3 and divide by 0.5. So I'm going to have 1 over 3 technically multiply by 0.5 because I'm dividing by it, equals k tilde to the 2/3. Okay, we're getting there. Maybe you want to figure out what, you want to neaten up that fraction slightly. So that's going to give us 2/3 equals k tilde to 2/3. And then remember, we want to undo this, so this is the same as this. Okay, and I'm going to put a g here, just to know that this is the golden rule level. And if you type that into a calculator, let me just do that, we're going to get two decimal places, 0.54. That is the steady state level of capital per effective worker in the golden rule. Just to remind ourselves what the steady state level was, our steady state level was 0.25, okay? So let me just quickly have a little look at what that looks like graphically. Okay, remember graphically, so for the old one, the one I just drew earlier that I'm now redrawing, I should have just kept it on screen. So what we had is we had our steady state level of capital per effective worker was here, But what we can see is that our steady state level wanted for there to be the golden rule, so you've maximised consumption, it wants it to be 0.54, so it needs to be more this way. Well, the only way that could happen is if this savings line crossed higher up. Okay, so let's say it crossed here, and in which case maybe this here is 0.54. So that's what that's saying. Well, what does that mean? That means if that's what you need to get to, you need to increase savings. You need to increase the savings rate in the economy. Okay, and that then maximises consumption. Now, it doesn't particularly look like it too much from this graph, it's just because I've drawn it quite badly. So yeah, that's how we maximise our consumption, because what there should be is if we drew a line tangential, it should be that that essentially comes tangential at that point there, but I have just drawn this very, very badly. But that's what this is saying. So that's a very quick run through of how you do it if you now have technological progress. As you can see, it really doesn't differ too much from what you already know. The key bit to remember is that the reason why this is great is because in terms of output per capita, we now have sustained growth, and we have sustained growth at the rate of G, which is the rate of technological progress. So I hope that helped you. I know that was very, very quick, but if you've watched my other videos, this shouldn't be too tricky.